We continue with another example of two variable statistics and linearizing data sets. So here we have two sets of data. Radius of circular motion, so I might assign that the variable capital R. Speed is often given the variable lowercase v. So let's linearize these. Let's check if they're linear and see what we can do here. So the first thing we check is, are both data sets on the increase? And they are. R is getting bigger, V is getting bigger. Okay, looks great. The next thing we check is proportionality or linearity. And we do this in our head. We say R here doubles from 0.2 to 0.4. What does V do? This is 0.8. Well, if it doubled, this would be 1.6. That doesn't look good to me. All right, let's check another one. All right, again, doubling. Let's go from 0.4 to 0.8 for R. What happens in the right column? 1.1 to about 1.6. Okay, that is not a doubling. Somebody is lagging behind. And who is that? And that would be this column here. The speed column is lagging behind. Because when we double, let's say R goes from 0.2 to 0.4, you can see that the speed doesn't quite double. This column needs some help. So what we do then is we square this column. So now we make a new column, we put a new variable, and we put a new unit that is going to reflect what we're doing. I've already done this, so we aren't going to waste time calculating this together. 0.6626, 1.302, 1.980, 2.522, 3.327. I'm squaring all the speed values, and finally 4.048. And once I've done that, I like to put a little line through that so that I'm not tempted to put that data now into my calculator. We are not going to put that data into our calculator. We've changed it. So V was having trouble keeping up, so we decided we were going to square him and help him out. Now let's check for linearity again. R goes from 0.2 to 0.4. That's a doubling. What do we have over here? 0.66 to 1.3. That's a doubling, isn't it? Let's check one more. Let's go 0.4 to 0.8 is a doubling. And what happens here? 1.3 to about 2.5. That's almost a doubling, isn't it? Right? That would be 2.6 if it were a perfect doubling. But this is data that has some error associated with it, right? Our ability to measure things is limited, but we are now on the right page. The next thing we do is we decide who's the rise and who's the run column. And the way you do that is you look at the units and you try and find a unit that makes sense to you. And if you take the meters divided by meters squared per second squared, what unit do you get? Or if you take meters squared per second squared and divide by meters, what unit do you get? Well, with a little thought, you'll see that what we want as our rise values is that unit divided by the run values. Slope is rise over run. And if we take that unit and divide by that one, we're going to get the unit meters per second squared, which hopefully is a unit you recognize as acceleration. So that's the best way to proceed here. These are going to be our X data values. These are going to be our Y points. We're going to put those into our graphing calculator. Stat, edit. You can see I've already put those into our calculator. The X values in L1, the Y values in L2. Quit. Go back into stat. Now we want to calculate linear regression. Enter. I've already put the X and Y values in where I want, so I don't need to fiddle with anything here. I'm just going to hit enter a few times. And this is going to give us our answer here. Y equals 3.4. I'll just round it to the same number of significant figures that radius was given. 2 sig figs, 3.4 x minus 0.047. But don't leave it as y and x. We want to put the variables that we have in this problem. So in place of x, we're going to put a capital R. So this is going to be 3.4 capital R, and instead of y, we're putting v squared. That's how you do it. Now, very often, this y-intercept will be a very small number, and that is the case here. So quite often, it's going to be perfectly okay to report our answer merely as v squared is equal to 3.4 times r. Sometimes they will ask you certain questions about what your data means. And what you need to do then is you need to match up this equation with some physics equation that hopefully you've run into in the class that you're taking. And one equation that we're going to run into in mechanics, very important equation, is that the centripetal acceleration is equal to v squared over r. And you can see here that if I put r next to the a sub c, I get r times a sub c is equal to v squared. So in this problem, circular motion, the centripetal acceleration is going to be 3.4. Let's put a unit on there. Acceleration is always meters per second squared. So they might ask you that extension question related to this data.